Hey, welcome back. This is college algebra. And today we're going to look at some applications of the exponential function, in particular exponential growth and decay. So especially now with the pandemic, mathematical modeling is a very active field of study. Let's take a look. So section 1, exponential growth, decay. We just want to look at the sort of standard formula which they use for modeling these scenarios. You'll get this formula in all kinds of different forms in your physics class, your chemistry class, and if you keep taking later math classes, you'll get it in differential equations and places like that. Okay, the a sub 0 is kind of your starting population. Okay, so initial population, and you can always get that just mechanically by plugging in 0 for t. So t is going to be thought of as time. T is some sort of time unit. And again, if you look at f of 0, you plug 0 into that equation, you'll get a sub 0 e to the k times 0, which is a sub 0. Anything times 0 is 0, so k times 0 will be 0. Now, it looks a little odd with that a sub 0, e to the 0. The a sub 0 is just like a name for something. So, you know, that 0 and its what they call subscript doesn't really, it's not like a computation. Okay, this is just a name for the initial population. Okay, anyways, e to the 0 then is just 1. So at time 0, this f of t thing equals a sub 0. Okay, and f of t can represent a lot of things. It can represent population at time t. It can represent an amount of a substance, so grams of radon, things like that. So usually they call it a population. The k thing then, what the heck is that? That's just some constant. Growth constant is what they usually call it, growth constant. And it can be found experimentally. People in the field, your researchers in the field will do some experiments and figure out what that constant is. We'll be finding the constants based off of kind of the problems in the book will give us the information, but that information normally would be given by the researcher in the field. So, I mean, mathematically, you are the one that's going to be determining the growth constant, but it's based off of research. Okay, so anyways, if k is greater than 0, that's going to give you the exponential growth. Okay? And in that case, your graph is going to look like this. Okay, where this point right here is going to be a sub 0. Okay, so literally on the graph, it's 0, comma a sub 0. Okay. If k is less than 0, then you're going to have exponential decay. So in that case, your graph will just be rotated about the y-axis, and it'll look like this. Okay, and again, this point here is going to be at 0, comma a sub 0. Okay, so let's take a look at some of the problems from the book. And take the problems you'll see in your homework. So they want you to build an exponential growth equation based off of some information. They give you your formula. So in general, you'll be expected to kind of have this formula memorized, but usually in the problem, they'll give it to you. So using that and some information about the change. So the question, I don't have it open, but it reads like, let me just get the question so I don't have to fake my way through this. All right, hold on. It's on page 505 if you have your book and you're kind of don't have anything to do right now, so I'm looking it up. Okay, so it says in 2000, and they give you a graph. Okay, but anyways, in the year 2000, the population. Okay, so there's an intro question about the size of New Jersey. Okay, so blah blah blah. The graphs show that there's like two graphs here. About the size of New Jersey, Israel has seen its population soar to more than 6 million since it was established. The graphs show that by 2050, Palestinians in the West Bank, Gaza Strip, and East Jerusalem will outnumber Israelis. Exercises 7 to 8 involve the projected growth of these two populations. So problem 8, part A. In 2000, the population of Palestinians in West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. Okay, so in the year 2000, we had a population of 3.2 million. Then it's estimated that by 2050, the population will grow to 12 million. Okay, so in 2050, the population grows to 12 million. We guess. Okay, we don't know. Use the exponential growth model, which is sitting right here. This is the exponential growth model. Use the exponential growth model in which t is the number of years after 2000. So they want t to equal the number of years after 2000. To find the exponential growth model that models the data. Okay. So what we have here with this stuff is really two ordered pairs. Okay. It's going to be t comma a, where t is the number of years after 2000, and a is going to be the population. Okay, so a represents the population in millions, t years after 2000. Okay, so these two factoids written as coordinates. The first one, 2000, is just 0. And the population 3.2, and then the second one, 50 years after 2000, the population is 12. Okay, so we're going to use these ordered pairs in order to solve for the unknowns in our exponential growth model. Okay. Off the bat, this thing tells us what a sub 0 is. This first ordered pair tells us the initial population. And if you don't believe that, you could literally plug in 0, 3.2 into the exponential growth model. So let's do that. Here again is the exponential growth model. And I'm going to plug in 3.2 for a, and then 0 for t. And again, it's, hey, look, it's 3.2 equals a sub 0. E to the k times 0 is the same as e to the 0. E to the 0 is just 1. So 3.2 equals a sub 0. So long story short, 3.2 is that initial population. Okay. So this allows us then to fill in the missing information in our formula. We now have 3.2 e to the kt. Right? So we just take this material and plop it into this formula, and it becomes a little more clear. Okay. Now we want to find that growth constant formula, and we could use this other ordered pair in order to do that. Okay. So now we take this ordered pair and plop it into this formula. Put the 12 in for a and the 50 in for t. And I'm going to reverse the k and the t, put the constant first. Okay, so this thing then is an exponential equation, and we can solve it, right? We'll isolate the exponential term, so I'll have 12 all over 3.2, and then you could take the logs on both sides. I use the natural log. Okay. So on the left side, the ln and the e cancel each other and you just have 50k. On the right side, you'll have ln of 12 all over 3.2. And then you just divide the solve for k. So k will equal ln of 12 all over 3.2 divided by 50. And now we can rewrite our formula as a equals 3.2e to the, and this is nasty looking, but it's better, in my opinion, than using some weird decimal approximation. Okay. Okay, so that's part A of the problem. Part B of the problem then, want you to use this formula in order to predict when Palestine's population will be 9 million. Okay, so part B, I guess, when will the population reach 9 million? In particular, in which year will the Palestinian population be 9 million? And what they mean by that is which year will the entire year it be over 9 million, basically. So if in 10 years, within that 10th year, all of a sudden it goes over 9 million, they want the 11th year. This is kind of a weird thing that ticks me off about the book, but I'm not going to get upset, okay? They want the year when it's officially over 9 million. So again, if it's year 10 and you're at 8.3 million, but then during year 10 it goes to 9 million, they don't want you to answer year 10. They want you to answer year 11. The first year where it's completely over 9 million for the entire year. Okay, so in which year is it completely? It wouldn't be an issue, but on the stupid homework on WebAssign or My Math Lab, it is. Sorry, I just woke up. Okay, I'm sorry. So, anyways, in which year is it completely over 9 million for the entire year? I mean, they should have it set up in My Math Lab. So, okay, I'm not going to go there. Okay, so you take our formula that we've constructed using all that data from our researchers, and you're going to let A equal 9 million. So let big A equal 9 and solve for T. And this is kind of the standard kind of song, if you will, that these problems have you go through. Okay, you'll solve out for the unknowns, and then you'll have a complete mathematical model that you'll use to answer some supplementary questions. Okay, 50 times t. Okay, so we got to solve for t here. And it's just an exponential equation. We want to isolate the exponential part, then do logs on both sides, yada, yada, yada. Okay, so 9 divided by 3.2 is e to the ln of 12 all over 3.2 all over 50 t. And then we can take ln's. I'm going to flip-flop sides. The ln of e, those cancel each other out, and you're left with ln of 12 all over 3.2 all over 50 t equals ln of 9 divided by 3.2. And then we want to solve for t, so multiply both sides by 50 all over ln of 12 all over 3.2. Okay, so times 50 all over ln of 12 all over 3.2. Okay, so we can pretend it looks like that and just multiply straight across. So I'm going to end up with 50 ln of 9 all over 3.2 all over ln of 12 all over 3.2, which is a nasty critter, but it's going to give you approximately 39.12 years. Okay, so again, this is that one little technicality I was talking about. They don't want the year then 2039 as their answer. They want the year 2040, because that's the year where at the start of the year you will be over 9 million in your population. Okay, so the end answer, Palestine will reach will be over 9 million in the year the year 2040. Okay, so it's one small technicality, and it's almost like when you go into my math lab, you may have to experiment. You may have to do the problem more than once. You know, the first time, guess 2039. The second time, guess 2040. Okay, okay. I apologize on behalf of everything. Okay, so let's hit the next problem. Here we're messing around with some plutonium. Plutonium-239 has a half-life of a lot, 25,000 years. You start out with 16 grams. And then they want to know how much is there after 25,000 years, then 50,000 years, then 75,000 years, then 100,000 years, then 125,000 years. Okay. Okay. Well, this one's kind of a silly question. You know, what is half-life? So half-life, if you're starting with a pile of plutonium, half-life is the amount of time required for the stuff to kind of evaporate. You can think of it as evaporating into half its size. Okay, so if you started with 16 grams, in 25 years, you're going to have 8 grams left over. Okay, or 25,000 years. Okay, so you can do it kind of in your head. After another 50,000 years, then you're going to have probably 4 grams left over. Because another 25,000 years will pass. Then after 75,000 years, you'll have 2 grams left, because another 25,000 years has passed. And then after 100,000 years, another half-life, you'll have 1 gram left. And then after 125,000 years, you'll have half of that, so 1/2. Okay, so you could go through and do it that way. These are all in grams. I mean, I don't see you could do it the hardcore way. You can go through all the math if you really wish. I guess we should talk about half-life and stuff like that. But that's going to be the answer. Let's do it the other way as well. Okay, so here they're giving you that in time 0 you have 16 grams, right? So using our math model, A equals A sub 0 e to the kt. Again, we know automatically that A sub 0 should be 16, right? E to the kt. And if you don't believe me, you can put in 0 and solve for A sub 0. Okay. Half-life is kind of, it almost tells you the next ordered pair, almost, right? It's not exactly giving you a time, though. It's just saying, well, it is giving you a time, right? It's saying in 25,000 years, half the original amount will be left. So in 25,000 years, you only have 8 grams left. So you basically get another ordered pair that'll allow you to solve out for that other unknown, the k value. So you'll have, and make sure you put the numbers in the right place, unlike me. You'll have a, this is t, this is a. So a is 8. On the other side, you have 16 e to the 25,000 times k, and then you could solve this equation for k, right? So you divide both sides by 16. There's 1/2, like half-life, okay? 25,000 k, and then you take the ln of both sides, and you end up with 25,000 k equaling the ln of 1/2, and then divide both sides by 25,000. You end up with ln of 1/2 all over 25,000, and now officially we have our new equation in all of its glory. A equals 16e to the ln of 1/2 all over 25,000 t. Okay, and then if you want to figure out how much is left after 25,000 years, it's not too hard to compute that. So 16e to the ln of 1/2 over 25,000 times 25,000. You're just plugging in 25,000 for t. Then you get 16e to the ln of 1/2 because the 25,000s cancel. Then e to the ln, those two will cancel each other out, and you get 16 times 1/2, which is 8, which is exactly what we got just doing it logically. So then if you try 50,000, what happens there, right? So in that case, you get 16e to the ln of 1/2 all over 25,000 times 50,000. And then, again, you get a nice cancellation in that exponent, ln of 1/2. The 25,000 goes in the 50,000 2 times. So you'll have e to the ln of 1/2 times 2, okay, which is the same as 16e to the 2 ln of 1/2. And then you could use the power rule, believe it or not, up in that exponent to bring the 2 inside. I mean, right now you can't cancel out the e and the ln. That won't work. They have to be kind of touching. Okay? So you'll have 16e to the ln to the ln of 1/2 squared, right? And then you can get rid of the e and the ln. You'll have 16 times 1/2 squared, which will be 16 times 1/4, which of course gives you the 4 that we got just by cutting 8 in half again above. Okay, so it's this game you play and you get all the rest of the answers. Let's not go there and do the other answers. Let's just leave it at that. Okay, if you allow me to, please. Let's just leave it there. Okay, so hopefully that. Well, no. Okay, let's do one more. I'm gonna do my job here. So let's try 125,000. So from our work above, after 125,000 years, we should have 1/2 gram left. Okay, so let's take a look. 2,000. We'll have 16e to the ln of 1/2 all over 50. No, it was 25,000 times 125,000. So that'll equal 16e to the 25,000 goes on 125,000 5 times, e to the 5 ln of 1/2. Okay, and then you use the power rule, bring the 5 inside the ln. You end up with 16 ln of 1/2 to the 5th power is really 1 all over 2 times 4, 8, 16, 32, 1/32. Whoops, and I lost my e somewhere. Let me smush them in there, sorry. So that will just be then 16 times 1/32, which of course is 1/2, which is what we thought it was. Okay, great. So the exponential growth models turn out not to be very realistic, okay? Because populations in general will not keep growing up and up and up and up and up and up and up forever, right? people eat all their food. There's competing species, so maybe there will be some wild pack of wolves eating all of the rabbits or something like that. So they could pop the rabbits. They reproduce all over the place, but if there's wolves around, they're going to start eating all those rabbits, right? And there's just no way for the rabbits to like grow unheated in the way that a exponential model would suggest. So what they come up with are these other models. And the first model that you're usually given is called the logistic growth model. And the thing about the logistic growth model is that instead of just zooming up, like instead of going up, 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 it's going to kind of curve over and level off. Okay, so you'll get what's called a sigmoid curve that looks like an S. All right, and then there's this limiting capacity up here, or limiting size, that the population will never exceed. Okay, so it's more realistic. Unfortunately, the formula is a little nastier. I won't expect you to have this memorized. 1 plus AE to the negative BT. It's also used in, if you're into computer science and that sort of stuff, it's used in machine learning. Okay, and when you're doing neural networks and you're trying to figure out if like a quote-unquote a neuron will fire, they use these functions to determine if the neuron fires. Okay. Okie dokie. So let's look at problem 37 from the book, and let me actually read it instead of faking my way through it. Okay. So 37. The logistic growth function, and they give us this function, f of t equals 100,000 all over 1 plus 5,000 e to the negative t. That thing describes the number of people, f of t, who have become ill with influenza t weeks after the initial outbreak in a particular community. Okay, so f of t equals the number of people with flu. I misspelled flu. With flu. T weeks after the initial outbreak. Okay. So you can imagine in a town of 100,000 people, there's no way for over 100,000 people to have the flu. Okay, so there is a limiting size involved if you're dealing with a population in a town, right? Okay, so how many people are ill at time 0? And you can even, these are fun to think of zombies and stuff like that. So how many zombies are there? Let's say number of people, number of zombies, right? Let's change this up a little bit so it's mildly interesting. The number of zombies T weeks after initial break. So how many zombies are there initially? Okay, so how do I figure that out? Well, you're just going to put 0 in for t, right? So times 0. We have 1 plus 5,000 e to the negative 0. Negative 0 is just 0. Okay, so that'll equal 100,000 all over 1 plus 5,000. And then that'll equal 100,000 all over 5,001, and that's approximately 20 zombies, or 20 people. Initially there's 20 zombies that have been released, probably by the government. You know, they're doing some experiment, and there's 20 zombies escaped from the lab. So how many are sick by the end of week 4? So how many zombies are there? How many zombies by the end of week 4. Okay. So clearly, again, you're just going to put 4 now into your given equation, and so you have 100,000 3 all over 1 plus 5,000 times e to the negative 4. Okay, and this is a good exercise for your calculator, making sure you can type this in correctly. What you'll end up with, you should end up with, is 1,080, about 1,080 zombies. Okay. What's the maximum number of zombies? Or what's the limiting size is what the book will ask for. The limiting size is always just going to be whatever the heck is in the numerator. Okay, so this object, the C value, is your limiting size. Okay, so in our case, the limiting size will be the 100,000, which is probably the population of the little town which is seeing the outbreak. Okay. I'll probably have to nuke it, right? It's the only way to get rid of those zombies. It's just to nuke the town. Okay, back to reality. Newton's law of cooling. Okay, so you may remember probably maybe it was 3 years ago, it was really cold during the winter. And what you could do, and I do not do this on your own, okay? What you could do is go in, get a bowl of water and put it in your microwave and heat it until it's boiling. The problem with doing this is I don't want you to do it is you could superheat the water or something, and then when you pull it out of the, I shouldn't even tell you that. Okay, so don't, do it on the stove or something. Boil your water, and then if you take it outside when it's super duper cold, you could throw it in the sky. You could throw the water up in the sky. Don't accidentally throw it on yourself; you'll get burned. But you can, no, do not do this. Okay, just do not do this. Throw it in the sky, and before it hits the ground, it will turn to ice. Okay, believe it or not. It's Newton's law of cooling is basically what you're looking at. It's saying that the rate of change of the temperature is proportional to the difference between the temperature of the surrounding medium and the temperature of the stuff that you're throwing into the air. Okay, so when you're throwing boiling water into a surrounding medium, in this case air, which is -5 degrees, the difference between those is so great, it is nuts. So the temperature change will astound you, and the water will literally freeze before it hits the ground. Okay, that's Newton's law of cooling as in terms of differences, right? And a lot of math you study in terms of slopes, okay, rates of change. From these rates of change formulas, you can produce these other formulas to make predictions. Okay, so anyways, that's the idea you want to have in mind when you're dealing with this law of cooling problem. Where does it come from? It comes from that. Okay, but anyways, the official formula is that the temperature is going to be equal to the medium's temperature, the surrounding mediums like the air, plus the temperature of the water minus the air's temperature times e to the kt. Okay, this is also important for foundries. My best friend was a foundry worker for years, and you have to know how long to wait before you take you get rid of the molding on the. So in a foundry, they pour hot metal into molds and form your casings for all kinds of good stuff, windmills and things like that. So you need to know when you can take it out of the molding, and you need to know how long it takes for the stuff to cool. to cool enough for that to be okay. So that's what this formula is telling you. Okay, so anyways, let's look at, T is the temperature of the object at time t. C is the temperature of the surrounding medium, which is usually just the air. And you think in terms of pizza. I think the problem we're going to look at is about pizza. T sub 0 is the initial temperature of the object. K is some sort of growth constant. Okay, so let's take a look. This is problem 48, and yeah, it is about pizza. Okay, so a pizza is removed from an oven that has a temperature of 450 degrees. It's left sitting in the room that has a temperature of 70 degrees. After 5 minutes, the temperature of the pizza was 300 degrees. Use Newton's law of cooling to find a model for the temperature of the pizza, T after T minutes. Okay, so they're saying the oven temp is 450 degrees. Okay. This is going to then be the temperature of the pizza at time 0. They're saying the room temperature is 70 degrees. This is the temperature of the surrounding medium, so that's C. And then they're saying after 5 minutes, oh geez, my writing. It's not my writing, it's the pen I'm using. There's a little button on it, and I keep hitting it, and it keeps, after 5 minutes, the pizza is 300 degrees. Okay. Okay. So the last point here. So these bullet points, I guess. The last bullet point is giving us an ordered pair. It's in this case time and then temperature. Right. So the time after 5 minutes, the temperature is 300 degrees. We also have some other ordered pairs here given. At time 0, the temperature is 400 degrees, 450. Okay, so it's like one of those exponential growth models where you have to figure out all the unknown constants. And yeah. Okay, so let's try to get our formula filled in. So again, the formula is T equals C plus T sub 0 minus C times e to the kt. Okay, so we're trying to fill in all the variables. So C is 70 plus T sub 0 is 450 minus C is 70. And then e to the kt. So the only thing we really have to worry about is that k, the temperature constant, I guess, the cooling constant. Anyways, we'll have 70, 450 minus 70. I think it's 3. What the heck is that? 380. So that'd be 380 e to the kt. Okay, and then we're going to use this ordered pair above, the 5, 300, in order to find K. So use to find our cooling constant, K. So we're going to plug that information into this formula. So the temperature then at time 5 is 300, so I'll have 70 plus 380 e to the 5K. I need to isolate the exponential part, so subtract the 70 over. I'll have 380 e to the 5k equals 230. Divide both sides by 380, so I have e to the 5k equals 23 over 38. Okay. Then take the logarithm on both sides, so ln of e to the 5k is just 5k. And then ln of course 23 over 38, divide both sides by 5, and you get your k value. Ln of 23 over 38 all over 5. So now we have a functioning formula for temperature, and all we need to know is the time, and we can tell you what the temperature of the pizza will be. Okay, so if you work in a pizza joint, probably a local pizza joint, this would be the formula you need to ensure that your pizza is still warm enough within health guidelines to be delivered. Okay, so part B, part A was just find the model. Part B then, what's the temperature of the pizza after 20 minutes? So literally you could just plug in 20 into this formula. Of 23/38 over 5 times 20. I did that in my calculator earlier. Let me find my answer. 121 approximately. 121 degrees. Then they want to know, when will the temperature be 140 degrees? When will temp be 140 degrees? So in that case, you're going to put 140 in for t and solve for little t, e to the ln of 23 over 38 over 5 times t. Okay, so move the 70 over. You're going to get 70 equals 380 e to the, the constant times t. Divide by 380 on both sides, so you get 7/38 equals e to whatever that constant was times t. ln on both sides, so you get the constant. Let's go ahead and put it back in there. ln of 23 over 38 over 5t equals ln of 7 over 38. Then you got to solve for t, so multiply both sides by 5 all over ln of 23 over 38. A lot of writing. Okay, and then we get our final answer. T is 5 ln of 7 over 38 all over ln of 23 all over 38. And you put that in your calculator and you get approximately 16.85 minutes, okay, before it hits that temperature. So maybe that's, that's the throw out time. You only got 16 minutes to get that pizza out the door. Otherwise, you got to throw it in the trash, right? Okay, so there's that. As usual, thank you for watching. That will complete this particular chapter. I'll do the review next, and then we'll have a test coming up as well. Okay, thanks for watching. Have a good day.